The question that I have is, could you do an example on friction involving a wedge? This is the problem that I have selected here. We have a beam, horizontal beam AC, that is supported on a pin at point A and on a wedge at point C. The wedge has an inclined plane at point C and is sitting on a horizontal plane at point D. These contact, that is the contact between the beam and the wedge and the horizontal plane, are frictional. The values of the coefficient of friction are given for these planes. The beam is subjected to a distributed load like shown in the picture. The question is to determine the value of the P needed to pull the wedge out. As we have done previously, the first step is to understand the mechanism so that we can mark the directions of the frictional forces and develop appropriate free body diagrams. So we start with the directions of the movements of the bodies involved. The horizontal plane over here is stationary, right? And the beam is being held by a pin at point A, and therefore that is stationary as well. When we pull the wedge out, the wedge is going to have a movement like shown by this arrow. Remember, we treat the wedge as a rigid body, and therefore every point on the wedge is going to be moving with that displacement vector, right? Now you can figure out the direction of the movement of a point on the wedge at this contact and of a point at this contact, right? And we do this by resolving the displacement vector along the contact planes, right? And it's easily seen that this arrow indicates the direction of the movement of a point on the wedge in that direction, right? And similarly, this is the direction of the movement of a point on the wedge along this plane. The frictional forces are going to be opposing the movement, and therefore this is the direction of the frictional force on the wedge on that contact plane, and therefore on the beam we're going to have a frictional force that is equal in magnitude and opposite in direction. And similarly, this is the direction of the frictional force on the wedge at that point, and therefore on the horizontal plane that is supporting the wedge, it's going to be in the opposite direction. Our second step here is to identify the bodies to be analyzed and draw the free body diagrams for these bodies, right? It's pretty clear that the bodies to be analyzed here are the beam and the wedge, right? Here are the free body diagrams for these two bodies. We already figured out the directions of the frictional forces, so we go ahead and mark the frictional forces in those directions. So I'm going to call this as F1, and therefore that also will be F1, and I'm going to call this as F2. Now we go ahead and mark the normal forces at these contact planes. So I'm going to call this as N1, and therefore this is going to be N1, and I'm going to call this as N2. This is a two-dimensional problem, and therefore at the pin over here at point A we have two support forces. So I'm going to call this as A sub x and call this as A sub y, and of course pin is incapable of supporting a moment, right? Let's also go ahead and replace the distributed load into equivalent point loads. So the logical thing to do here is to take the distributed load and subdivide this into two triangles and a rectangle. Here is one triangle, here is the rectangle, and here is the other triangle. The magnitude of the point load associated with this triangle is the area under the distributed load, which is half times 3 times 50, 75 pounds. We note the area under this triangle is identical to this, and therefore R1 and R3 are equal to each other. The area under the uniform part is 50 times 5. This is 5 right here, that's the length. And the intensity here is 50 pounds per linear foot, and therefore the point load associated with that, R2, is 250 pounds. R1 is acting at the centroid of this triangle, which is 1/3 from the base, right? And therefore this distance is 1 foot. R2 is acting right in the middle of the rectangular part, and therefore this is 2.5 feet and this is 2.5 feet. R3 once again is acting at the centroid of this triangle, which is 1/3 from the base, and that's 1 foot, and 2/3 from the vertex, which is 2 feet, right? Now let's go ahead and develop a strategy for solving the problem. We list the unknowns and we figure out where the equations are going to come from for solving the unknowns. Between the two free body diagrams, these are the unknowns, right? Ax, Ay, N1, F1, N2, F2, and P. So we have a total of 7 unknowns. We can write down 2 force equations and 1 moment equation for the beam, so that'll give us a total of 3 equations for the beam. We can write down 2 force equilibrium equations for the wedge, right? And then we have 2 friction equations, one for this interface right here and another one for this interface right there. So we have a total of 7 equations, and therefore the problem can be solved. Here are the equilibrium equations associated with the beam, 2 force equations and a moment equation. In equation 1, we sum the forces in the positive x direction and set it to 0. Ax goes in as a negative term. It's already in the x direction. And F1 needs to be resolved in the x direction. So that will be F1 cosine 20 degrees, because this angle is 20 degrees right there. And the F1 cosine 20 is going to be a positive term in this equation. The horizontal component of N1 is N1 sine 20, and it's acting in the negative x direction. So that goes in as a negative term. That's about it. All of these forces are perfectly vertical, and therefore they don't have any horizontal components. So that includes the reaction at point A in the y direction as well. Here is the force equation in the positive y direction. I'll let you follow that. You can take the moment about either point A or point C. Here I have chosen to write it down about point C. Taking the counterclockwise moment as positive, the moment associated with 75 pounds is 75 multiplied by 2 feet, right? So that's a counterclockwise moment, so that goes in as a positive term in that equation. 250 multiplied by this distance, which is 5.5 feet, is another counterclockwise moment. 75 multiplied by this distance, which is 9 feet, is another counterclockwise moment. AY multiplied by the length of the beam, which is 11 feet, is a clockwise moment. So that goes in as a negative term. The lines of action of the remaining 3 forces, which are N1, F1, and AX, are passing through point C, and therefore they do not make a contribution to the moment equation here. Here are the 2 force equilibrium equations for the wedge, and they're pretty easy to follow, so I'll let you follow. Finally, here are the 2 friction equations. One of them, the first one, is written for this interface. F1 equals coefficient of friction multiplied by N1, where the coefficient of friction is 0.2. The second one, which is this one, is written for this interface. F2 equals coefficient of friction of that interface multiplied by N2. The coefficient of friction of that interface is 0.4. So that's it. We have derived the 7 equations we set out to derive. So let's go ahead and solve these equations with the objective of answering the question, which is to find a value for P, right? For convenience, I brought all 7 equations and listed them on this page. My strategy is the following. First, I'm going to find AY from this equation, equation number 3. Then I'm going to find N1 from equation number 2 and N2 from equation number 5. And of course, in doing that, I need to relate F1 to N1 using the friction equation. Once I have values for N1 and N2, I will then go ahead and use equation number 4 in order to find a value for P. Once again, I need to use the friction equation to relate F2 to N2. So it seems like I don't really need equation 1 at all to answer the question here. But of course, if I want to find a value for ax, I need to use equation number 1, right? All right, let's briefly go through this. Here is ay evaluated from equation number 3. Next, I want to find n1 from equation number 2. And these are the two terms that involve n1. And I'm going to use the friction equation, which is F1 equal 0.2 multiplied by n1, in order to express this in terms of n1. Then I factor n1 out of the two terms, so n1 multiplied by 0.2 times sine 20 plus cosine 30 equals, right? We bring everything else to the right side. So this, the three terms here, they go to the right side like that. And then of course when ay goes to the right side, it becomes minus ay. We now have a value for ay, so you substitute that, and that becomes equal to 200. Solving that equation for n1, we get a value of 198.4 pounds for n1. Now we use equation number 5 in order to find a value for n2. Expressing F1 in terms of n1 and rearranging, we get a value of 200 pounds for n2. Finally, we go ahead and find a value for P from equation number 4. So I get a value of 49.5 pounds for P. So this is how much force you need to apply in order to pull the wedge out.